This is question number 6 from the review packet. The problem reads, a circuit contains 2 resistors, 10 ohms and 20 ohms, 2 capacitors, connected to a 6-volt battery as shown in the diagram. The circuit has been connected for a long time, so that statement right there is actually pretty important. So you've probably seen it a few times now. We recognize that if it's been connected for a long time, that I've got a bunch of charge building up on the upper plate here of the 12 microfarad capacitor, which means that current no longer flows in order to charge that, and current in the circuit simply flows through both the 10 and the 20 ohm resistors, not flowing through the A to B leg for the capacitor. So the blue line shows kind of the current path, and once we're at steady state, we can see then that it's basically a series circuit. So the first question says, first, calculate the total capacitance in the circuit. You should recognize that capacitors these capacitors are in series, so finding the total capacitance will follow the formula 1 over the equivalent capacitance is equal to 1 over C1 plus 1 over C2. In this case, I've got 1 over 12 microfarads plus 1 over 6 microfarads. I will find a common denominator of 12, and I will get 3 over 12 is equal to 1 over the equivalent capacitance. And once I deal with that, I get an equivalent capacitance of 4 microfarads. So that's our answer to the first part, which is the equivalent capacitance of the the capacitors in series. Next question is calculate the current in the 10 ohm resistor. This is awesome. You know, I've got a basically series circuit, so the total resistance is R1 plus R2, or 30 ohms in this case. I've got a voltage of the circuit is 6 volts, so using Ohm's law, V equals IR, solving for total current, I get voltage over resistance, or 6 volts over 30 ohms. Let's call that 1/5 of an amp, or 0.2 amps. There's our answer for part B. Moving on to part C, they want to know the potential difference between point A, which is right here, and point B, which is right here, which is the same as the voltage drop across the 20 ohm resistor. It's a little bit more difficult to see when you look at it in terms of the capacitors here, but electrically A and B is the same as the voltage drop across here if this were some sort of a voltmeter. So that's what I'm going to do, is I'm just going to find the voltage drop across the 20 ohm resistor. I'm going to use V is equal to IR, where I is the current that I just figured out, the total current, 0.20 amps, or 200 milliamps, times the resistance value of 20 ohms of that last resistor, and I get a drop of 4 volts across the 20 ohm resistor, which means that the potential difference between A and B is 4 volts. Okay, moving down, part D, the charge stored on one plate of the capacitor. Let's take a quick look here. The capacitor network, the capacitor network up here at the top is 2 capacitors in series, and therefore the charge on one plate is equal to the charge on another plate. Well, since this is behaving badly, let me just do this. Okay, so the charge Q up here on the upper plate of that 12 microfarad capacitor is going to be the same magnitude, obviously opposite in polarity to the charge on the bottom plate. And on the 6 microfarad capacitor, I can say that I'm going to have the same charge Q, even though I have a different capacitance here. That's due to the difference in potential across that 6 microfarad capacitor. Regardless, I should recognize that all of these charges are all Q with simply differences in polarity. So the charge is the same on all of these different capacitors. That's an important point, and therefore the charge is the same on the equivalent capacitor. So let's go back down to our problem. What I'm going to do to solve this is basically use my general equation for the relating charge and voltage and capacitance, Q equals CV, where C is going to be the equivalent capacitance. And the reason that I chose this is because I know the voltage drop across that 20 ohm resistor, which is the same as the voltage drop across the equivalent capacitor network in series. So V that I found in this problem right here of 4 volts is already known The equivalent capacitance is already known. That's the 4 microfarads. So I can find the charge on each plate. Doesn't matter which plate of the capacitor I'm talking about. So I'm going to multiply then 4 microfarads, and I'm going to multiply that by my voltage of 4 volts, being the difference of potential between points A and B, and therefore my units are going to be microcoulombs. So 4 times 4 is 16, but I've got to deal with this prefix here, so I've got 16 microcoulombs being the answer to part D. Part E, if the wire is cut at point P, will the potential difference between A and B increase, decrease, or stay the same? No charge is flowing when you're at steady state. Once point P is cut, nothing changes. The circuit continues to behave as it had before that was done. The capacitors do not discharge, therefore we can say that the current remains the same because they're not discharging.